This is AI with Justin. The previous video in this series covered the progression from the standard Boltzmann machine to the restricted Boltzmann machine, why and how this improvement reduced the training cost, some use cases for RBMs, and finally alluded to how the success of the RBM encouraged the subsequent research into deeper latent representations, which is the topic of this video. I'll be explaining what deep Boltzmann machines and deep belief networks are, how they're trained, and introduce challenges associated with building deep latent representations. First, let's do a short overview of the general architecture of these two models. Deep Boltzmann machines expand upon restricted Boltzmann machines by adding additional hidden layers. The architectural properties of entirely symmetrical edges, as well as no connections between nodes in the same layer, are retained. Deep belief networks architecture is also similar, except differs in that at the end of the training, only the top two layers are connected symmetrically. The rest are directed towards the visible layer. To understand why the networks have their structural differences, we'll need to explore how they are trained and how they are used. Let's explore training methods first. While backpropagation was invented prior to the development of these networks, it had not yet gained widespread popularity for end-to-end training, for a variety of reasons. Instead, DBM and DBN training was most commonly associated with Layerwise training and/or wake-sleep training, with DBNs often combining the two. Layerwise training is relatively simple. One hidden layer at a time is trained identically to how RBMs are trained. So essentially, the algorithm just stacks RBMs on top of each other, where the previous RBM's output is the input for the next RBM. This algorithm was valuable, 1, because it was fast compared to other methods, and 2, because it's a very consistent and stable training algorithm. To expand on this, Layerwise training has a variational lower bound, which essentially means each layer added will either improve the representation or at least not make it worse. Note that this guarantee is contingent on each layer having the same number of nodes. While Layerwise training is effective at consistently finding acceptable local minima, it is not good at tuning for more optimal minima. In other words, Layerwise training tends to underfit the data. While it's less consistent and stable, the wake-sleep algorithm has the potential to learn more optimal representations than Layerwise training. In the wake-sleep algorithm, there are two sets of directed weights. One set, the recognition weights, connects the input layer to the highest or deepest layer. The other set, the generative weights, connects the deepest layer back to the input layer. Much as the name entails, there are two phases to the algorithm, the wake phase and the sleep phase, which are cycled back and forth between. During the wake phase, input is provided and propagated up through the recognition weights. At each layer, the generative weights are adjusted using the gradient to increase the probability they would recreate the state in the layer below. During the sleep phase, the same process is repeated, but in the opposite direction. Using the values generated by the opposite weight set is a brilliant way of estimating the gradient of the variational bound, and allows the algorithm to retain a local learning structure while using gradient-based learning. But it is this same property that also leads to the wake-sleep algorithm's major weaknesses. The gradient estimate inferred by the algorithm is just that, an estimation. There is no guarantee the algorithm will successfully follow a desirable gradient. One phenomenon which can lead the algorithm astray from the desirable gradient is the explaining away effect. Because of the algorithm's local learning structure and reciprocating self-supervising deep networks, hidden causes which ideally should be independent can become dependent. This can cause the network to find an intermediary solution, which is known as mode averaging. At the end of deep belief network training, or sometimes as the network is grown, the recognition weights up to the second highest layer are dropped from the network. The deep belief network is able to drop these weights because its usage differs from a deep Boltzmann machine. I'll explain this difference next. Both DBMs and DBNs are generative networks and can act as content addressable memory systems, but they do this in slightly different ways. To generate data from a DBM, we can provide it with input, propagate all the way up and all the way down through the network, and it should produce data fitting the distribution it was trained on. A deep belief network generates data by receiving an input at its highest layer, performing iterative passes between its top two layers, also known as give sampling, then eventually propagating down the rest of the network. Both networks can also be fine-tuned to perform classification and regression. Essentially, the same use cases as mentioned in the previous video for RBMs also exist for these deeper variants. So if the use cases don't change, why use multi-layered networks anyways? In short, having many levels of nonlinearities allows deep networks to represent highly nonlinear and highly varying functions. Expanding the depth rather than the width of a network better enables abstraction and generalization. Forming abstract representations which are both specific enough to be valuable and general enough to not simply be a memorization is a difficult task. While increasing the size and depth of a model allows it to represent more complex distributions, it also increases the complexity of training a model to do so successfully. At the time DBMs and DBNs were popular, training them to form quality representations was often finicky and unreliable. In the next video, I'll be presenting a handful of training techniques designed to stabilize training by incentivizing the formation of valuable latent representations. While many of these concepts can be applied to many categories of models, I'll be introducing them as they are applied to autoencoders. If you enjoyed this video, please give it a thumbs up and consider subscribing.